Okay, morning class. Before I start the class, I want to show you this book. This book is written by a lecturer from FTK. So this book contains numerical methods topics, and since our EM1, it contains numerical and also analytical parts, two parts. So the non-numerical, this means the analytical part will be given through email, okay, in soft copy. Okay, this book is not compulsory, okay, not compulsory. So I'll just pass around for you guys to have a look. So if you are interested to buy this, the price is 30 ringgit, 30 RN 30. So later on, I will send a link into the WhatsApp group for those who are interested to buy this book. Okay, so I pass it around with you guys to have a look. Okay, not compulsory, not compulsory. Okay, today we will look at this matrices, okay, but solution of linear systems. Okay, this is under numerical parts, okay, numerical methods. And the learning outcomes are, upon completion of this lesson, you should be able to reduce a matrix. Okay, we will reduce a matrix into raw echelon form, REF. Okay, into REF. This means raw echelon form by using the raw reduction method. Okay, and then we will look at how to solve a linear system by using three different methods. Okay, the first one is Gauss elimination. Okay, the second one is LU decomposition, and the third one is Gauss cycle. Okay, we will look at how these three methods are used to solve a linear system. Okay, so system of linear equations. That means linear system. Okay, this is a linear system. Linear system is a collection of linear equations. Okay, these are the three linear equations. Okay, there are three linear equations now. Okay, linear equations means the equation is linear where x, y, z, they are all in power of 1. Okay, power of 1. That's why this is a linear equation. So when you have a collection of linear equations, it makes up a linear system. This is a linear system. And it involves a set of variables. Variables means x, y, z. Okay. So for example, from this linear system, we can present this into the form of ax equals to b. Okay, ax equals to b. The a extracted from the here 3, 2, minus 4. But first of all, you have to make sure the x, y, z. Okay, there are follow. Okay, they are in order. Okay, they are in order x, y, z, x, y, z. Then you extract the coefficient of the x, y, z. So 3, 2, negative 4. You have 3, 2, negative 4, 2, negative 4, 1. Okay, and 1, 3, 5. And the variable x, y, z, you put it here, x, y, z. Okay, and the right-hand side value, okay, it forms a vector. Okay, so this is a matrix form. Okay, this is a matrix form. And the solution to this linear system is presented in vector form as well. Okay, that means x equals to 1, y equals to 2, z equals to 1. Okay, so for linear system, actually, we can check. Okay, after you obtain the solution, you can check whether the solution is correct or not. That means you just substitute x is 1, y is 2, z is 1 into this. You will get 3. Into this, you will get negative 5. Okay, when you substitute into this x, y, z, you get 12. Okay, if all these values are correct, that means your answer is correct. Okay, this is how we check the solution for a linear system. Okay. Now look at this ax equals to b. Okay, this x and b, they are in bold. Okay, in bold. So when we write the x, okay, we will need a symbol, okay, a symbol, something like this underneath to present this as a vector x1, x2, x3. Okay, without the symbol, that means this is just an x, okay, just an x. But in computer, when we type, we make it in bold. That means this is a vector. Okay, this is a vector, something like this. But when we write, that is impossible for us to draw like that. So just insert a symbol. Okay, so x is this, b is b1, b2, b3, the right hand side value from the linear system. Okay. Okay, so this is a big picture solution of linear systems. Ax equals to b. So for a problem of Ax equals to b, we can solve this numerically by using these three methods. Okay, we will look at this one first, Gauss elimination. Okay, to use this, we need to know how to row reduce a matrix. Okay, row reduce a matrix. The second method, we will look at it will be LU decomposition. Okay, LU decomposition. We will decompose A into L and U. Okay, then we apply forward and backward substitution to get the solution. And the third method, Gauss cycle. Okay, to apply this method, there's one condition. Okay, there's one condition. The matrix A must be strictly diagonal dominant. Okay, then only we can apply this method. And after that, we will run the iteration to get the x, y, z. Okay, so the solution that we obtain through this methods, it could be exact or approximated solution. It depends on the linear system. Okay, it depends on the linear system. So now we look at this Gauss elimination. But before this, you have to know how to row reduce the matrix. We look at the elementary row operation first. Okay, this operation is used to row reduce a matrix into an upper triangular matrix. So given a matrix, we will row reduce until we get something like this. This is an upper triangular matrix. Okay, upper triangular matrix, meaning that the lower part is 0, all zeros. Okay, I call this as staircase. Okay, I call this as staircase. So all entries underneath the staircase must be all zeros. It must be all zeros. Okay, and this one, it could be any values. Okay, it depends. And pivot. Okay, there are two names. Okay, either we call it as pivot or leading. Okay, these three. The one stay at the corner of the staircase. Okay, it's called either pivot or leading. So throughout this chapter, I will call it as pivot. Okay, as leading normally is used when the value is all in 1. Okay, that is leading 1. Okay, and normally leading is used when we want to row reduce into row reduce echelon form, RREF. But this is just REF. We just need to row reduce until REF. Okay, not RREF. If RREF, we have to use leading 1. Okay, pivot, it could be any values. Okay, as long as it is non-zero. Pivot must be non-zero. Okay. Now there are 3 types of operation to row reduce a matrix. Okay, the first one is we can interchange any 2 rows. Okay, when we want to interchange any 2 rows, we use this symbol. Okay, and 2 arrows, okay, in both directions. This one means interchange. We change row I with row J. So for example, this one, okay, the first, okay, this one, the top of the left, okay, top on the left hand side, this one, it should be a non-zero. Pivot should be non-zero value. Okay, if this is 0, that means we need to swap the row. Okay, so we swap row 1 with row 2. So row 1 will be swapped into row 2. Row 2 will be row 1 now. After the swap, okay, after you swap row 1 with row 2. Okay, the second type of operation is we can multiply any row with a scalar. Okay, so this is normally used when we want to raw reduce into RREF. Okay, so since now we just need REF, the raw echelon form, so we don't really need this. Okay, but I still introduce this one. Okay, this one is just we because the pivot, when we want to get the leading one, when this one we need to change into one, we have to divide this by 2, right? So we need to multiply half 1/2 to raw 1 in order for us to get 1 here, if we want to get the leading one. Okay, so 1/2 times raw 1, that means all raw 1 entries must be multiplied to half. So you have 1, 2 as a result, and no changes on the raw 2. Okay, this is the second type of operation. And the third type is the most frequent use operation, MRI plus RJ. This is called as raw replacement operation. Okay, we replace the raw by an operation. Okay, for example, this one, this is the given matrix. Okay, the top on the left hand side, this one, it should be a pivot. Okay, if this is a non-zero entry, that means this will be the pivot, the first pivot. Okay, after you identify the pivot, okay, the entries underneath the pivot must be all zeros. Okay, it must be all zeros. So we need 2 operations to change these 2 rows. Okay, we want to change these 2 into zeros. Okay, we look at the first operation. Okay, the operation, it will always be written in this way, MRI plus RJ. Okay, M is a constant. Okay, it's a constant. RI is the pivot row. Okay, pivot row. RJ is the row that you want to change. Okay, you don't have to write this one. This one is just means that we replace row J by this operation. Okay, if you look at this one, it means that row J will be changed in the next matrix. There is no changes on row I, but row J will be changed in the next matrix. And this symbol, it will always be plus. No minus, it will always be plus. Okay, no matter what you use before this, maybe some of you learn Ri minus a constant multiplied to Rj or whatever. Now I want you to follow this one, MRI plus Rj. This is always a plus. And row J is the one that will be changed in the next matrix. Okay, strictly follow this one. Okay, now we look at this. We want to make use of this pivot to change this one into 0. Okay, so how to get an M? Okay, there is one formula to get an M. M equals to negative. Okay, there must be a negative fraction. Okay, negative fraction. The pivot value, you put it at the bottom. The value that you want to change into 0, you put it at the top. So you have -3. Okay, -3. So there's a -3 here. -3 R1. Why R1? Because your pivot comes from row 1. Okay, so -3 R1 plus, it will always be a plus R2, because the value that you are going to change into 0 comes from row 2. So you have -3 R1 plus R2. Okay, next one, another operation to change this one into 0. Okay, so we need to compute for M. So M again equals to a negative fraction value. Okay, negative fraction. Okay, pivot stay at the bottom. The value that you are going to change into 0, you put it at the top. So minus, you get a plus 2. Okay, +2. So that's why you have a +2 here, +2 R1, because you are using this pivot. You are using this pivot comes from row 1. So 2 row 1 plus row 3. This is from row 3. Okay, once you have construct this, okay, you have identified the operation. Okay, next we can write the new matrix. Okay, so according to these operations, we know that only row 2 and row 3 will be changed. Okay, only row 2 and row 3 will be changed. Row 1 remain the same. So there is no changes on row 1. 103 is still 103. Okay, and for the second row, okay, we have to apply the first operation. So this means -3 multiplied to the whole row 1, and then you need to plus into the row 2 respectively. Okay, so we go through this one by one. Row 1. So 1 times -3, you have -3. -3 plus into row 2, you get 0. Okay, 0 times -3, you get 0. 0 plus 5, still 5. Okay, 3 times -3, -9. -9 plus -2, -11. Okay, same goes to the second operation to change the row 3. Okay, so this one, row 1. 1 times 2, because 2 times row 1. So 1 times 2 plus into row 3. Okay, so 1 times 2, 2. 2 plus -2, you get 0. Okay, 0 times 2, 0. 0 plus 1, 1. Okay, 3 times 2, 6. 6 plus -3 was 15. Okay. Okay, next. Okay, this one I haven't teach you how to look at the staircase. Okay. Before I continue, I show some example first. Okay, because you have to know how to sketch. Okay. For example, I just simply give one example. 1, 1, 0, 2, -1. 0, 2, 3. 0, 0, -1. Okay, when we sketch the staircase, okay, you have to know how to sketch. Okay, so the first one is the non-zero. So this is the pivot. Okay, this is the pivot. So one line, okay, one horizontal line, you put it here, and those entries under the line should be all 0. Okay, so as you cross this, okay, this is a non-zero entry. So it needs to go down. But after you cross one unit, okay, this one needs to turn right. Okay, turn right. Okay, now this is again a non-zero, so it goes down. Once goes down, cross one row. When this vertical line cross one row, you need to turn right. So this is the staircase. This is in REF. This is raw echelon form. Okay, this is raw echelon form. I give another example. Let's say 110, 2, 1, 3, 0, 1, 1. Okay, this is not REF. Okay, this is not REF. Why? This is the pivot. Okay, this is the pivot. Suppose you should have a line here. Okay, but this is not 0. So what you need to do, you need to come up with one operation to change this into 0. Okay, just one operation is needed because this is already in 0. So we don't have to change this row 3 anymore. Okay, we just need to build with the row 2. We need to change this into 0. Okay, and let's say after the operation, the row 2 is changed into this one, this one. Okay. So now we continue. Okay, after this line, this is non-zero, so we need to go down. After you cross one row, this vertical line, after you cross one unit, it must turn to the right. Again, this is the pivot. So the entry underneath should be 0. So now we need to use this pivot to change this into 0. Okay, this is the process. Okay, so we need to change this one into 0. Okay, another example. Let's say you have this. This one. Okay, this is the pivot. Okay, cross. Up to here, these are all zero. So you can cross one more. For horizontal line, you can passing through more than one column. Okay, you can pass through more than one column, but for the vertical line, after you pass through one row, you need to turn right. Okay, these are the difference between the horizontal and vertical line. Okay, so now you see all the entries underneath the line must be zero. Okay, this is a non-zero entry, so this is the next pivot. So this goes down. After you cross one row on the right. So this is REF. This is row echelon form. Okay, this is row echelon form because underneath the staircase, all entries are zero. Okay, one more example. Let's say 0, 0, 1, 0, 0, 2, let's say. Is this REF? Okay, let us check together. Okay, all zero, cross until here. This is pivot, right? Yeah. So we need to go down one unit, then turn right. This is not zero. So we need to use one operation. Okay, that means this is the pivot. We use this pivot to change this into zero. Okay, after this change into zero, this is REF. Okay, but for the case, okay, for the case of this chapter 1, all staircase will be in this form. Okay, because the solution from this chapter 1 is unique. Okay, unique. Unique means when your staircase, when you have this is the pivot, pivot, pivot. You have 3 rows. Okay, you have 3 variables, and you have 3 pivots. That means the solution is unique. The solution of the linear system is unique. Unique means one solution. You have only one solution. But for this kind of case, for this kind of case, you have more than one. The solution is not unique. You have more than one solution for this kind of case. Okay, but what you are going to learn under this chapter, everything will be something like this. Okay, we look at the case with unique solution. Okay, that's why the staircase will be like this. Okay. Any questions? Any questions on this? You need to know how to sketch the staircase in order for you to know how to row reduce the matrix. Any questions on this one? Okay, now we go back to the slide. Okay, and we continue from here. So now, when you sketch for the staircase, okay, there is one horizontal line here, and when you see this non-zero entry, we go down one unit and we need to turn right. So this should be zero. Okay, this should be zero, and this is your second pivot. Okay, we use the latest pivot. Okay, so this is the pivot. This is the one to be changed into zero. So your M is negative fraction pivot stay at the bottom. The value, the entries that you want to change into zero, put it at the top. That's why you get a negative 105. Okay, so negative 105 R2. R2 because your pivot comes from row 2 now. Okay, row 2 plus row 3. This comes from row 3. Okay, so this one means only row 3 will change. Only row 3 will change. Row 1 and row 2 remain the same. So you copy the first row, second row, and you put them here. Okay, we just change the row 3. Okay, 0. Okay, 5 times this, you get negative 1. Negative 1 plus 1, 0. Negative 11 times negative 105, that's mean 11 over 5. 11 over 5 plus 3, you get 26 over 5. Okay, so this is the raw echelon form. So we stop here. Okay, this is the raw echelon form. Okay. Any questions? Any questions for the raw reduction? No. Okay, then we look at one example. Okay, reduce the matrix into raw echelon form by using only raw replacement operation. Okay, we use only raw replacement operation. Okay, the MRI plus RJ. Okay, this is the given matrix here. So this is the pivot. Okay, this is the pivot. We want to change 2 and 1 into 0. So we need two operations. Okay, we need two operations. Okay, the first M is negative fraction. Pivot stay at the bottom. The value that you are going to change into 0 is to put it at the top. So that's why minus minus you get a positive 2. Okay, so you have 2 here. 2 R1. Row 1, pivot from row 1. So 2 R1 plus R2. Okay, R2 here. This one from row 2. And to change this into 0, okay, negative, do not forget the negative fraction. The pivot is still negative 1. Okay, the pivot is still negative 1. We use the same pivot to change this 2 into 0. Okay, so the value that you want to change into 0 is 1. So negative, you get a positive 1. Okay, positive 1. That's mean 1 R1, 1 times R1. So we just write R1. R1 plus R3. Okay, so row 2 and row 3 will change in the next matrix. No changes on row 1. Okay, the pivot row will not change. Okay, so negative 1, negative 1, 2, negative 5. You just copy the first row. And for the new second row, okay, you have to apply this operation. So 2 times row 1. Okay, row 1. Negative 1 times 2, negative 2. Negative 2 plus 2, 0. Okay, 2 times 2, 4. 4 plus negative 1, 3. Negative 5 times 2, negative 10. Negative 10 plus 6, negative 4. Okay, and the second operation, R1 plus R3. That means row 1 plus into row 3, respectively. So this one plus this, you get 0. 2 plus 1, you get 3. Negative 5 plus 3, you get negative 2. Okay, then, okay, when you sketch the line, okay, this is the horizontal line. Okay, you see a non-zero entry, so it goes down. It goes down, then you need to turn right. So that means this is the pivot, and you need to change this into 0. Okay, so your M will be negative fraction. Pivot is 3. The value that you want to change into 0 is also 3. So you get negative 1. So you have negative 1 R2. Okay, your pivot comes from row 2 now. Okay, this is the pivot now. Pivot from row 2. So negative 1 times row 2. We just write negative row 2. Okay, negative row 2 plus into row 3. Okay, so only row 3 will change. Row 1 and row 2 remain the same. So you just copy the first and second row here, here. And then the last row, we use this operation. So negative 1 times row 2. Okay, so all this multiply to negative 1 and then plus into the third row. Okay, 0 times anything plus into 0, still 0. Okay, no changes. So normally we start from the pivot column. Okay, so this one, negative 1, 3 times negative 1, we have negative 3. Negative 3 plus 3, 0. Okay, negative 4 times negative 1, we get positive 4. Positive 4 plus negative 2, we get positive 2. Okay, so this is the REF. raw echelon form. Okay, any questions? Now we look at one more example. Okay, another matrix. This is the pivot. Okay, this is the pivot, and we want to change these two into 0. So your M will be negative fraction. The pivot is 2. Pivot is 2. The value that you are going to change into 0 is negative 2. So cancel out the 2, minus minus, you get positive 1. Okay, positive 1. That's why you have positive 1, R1. Pivot from row 1. So 1, R1. That's why we just write R1. R1 plus into R2. Okay, and the second M. Okay, we want to use this pivot to change this into 0. Okay, so your M is negative fraction. Pivot is still 2. And the value that you are going to change into 0 is 1. So you have negative half. Okay, negative half multiplied to the row 1 because your pivot from row 1. Okay, negative half row 1 plus row 3. Okay, so no changes on row 1. Row 2, row 3 will change. Okay, so 2 to 3, row 1, no changes. Then row 1 plus row 2. So this one, row 1 plus into row 2. 2 plus negative 2, 0. 2 plus 1, you get 3. 3 plus 5, you get 8. Okay. And for the new row 3, this one, negative half, multiply to row 1. Multiply to this row 1. So 2 times negative half, you get negative 1. Negative 1 plus 1, 0. Okay, 2 times negative half, you get negative 1. Negative 1 plus 3, positive 2. 3 times negative half, you get negative 3 over 2. Negative 3 over 2 plus 4, you get 5 over 2. Okay, so when you sketch the line, okay, this is the horizontal line. Okay, non-zero, it goes down, and you need to turn right, meaning that this is the pivot. This one should be 0. Okay, so next M is negative fraction. The pivot is 3. Remember, pivot stayed at the bottom, and the value that you want to change is 2. So you have negative 2 over 3. Negative 2 over 3, row 2. Row 2 because your pivot from row 2 now. Okay, row 2 plus into the last row, row 3. Okay, so only row 3 change. Row 1 and row 2 remain the same. Just copy row 1, row 2, copy. And the last one, okay, this one. Okay, so 3 times negative 2 over 3. Negative 2. Negative 2 plus 2, 0. 8 times this, negative 2 over 3 is negative 16 over 3. Negative 16 over 3 plus 5 over 2. Okay, you get negative 17 over 6. Okay. Okay, this one you need to try in order for you to identify whether you understand it or not. Okay, so we try this now. We try this together. We haven't signed for your attendance. Anyone? Okay, this row reduction is very important because for Gauss elimination, you need this. Okay, and also for LU decomposition, you can also use this. Okay, so you must know how to reduce the matrix into RM. So we have the pivot. First one is the pivot. What is your first operation? R1 plus R2. Okay, R1 plus R2. Okay, I will show you how to get an M. Okay, your M is negative fraction. The value of pivot is 1. Stay at the bottom, and the value to change into 0 is -1. Put it at the top, so you get +1. So +1 R1. Okay. And what is the second operation? Huh? What is the second operation? -5 R1 plus R3. Yes. Okay, because your M is negative fraction, the pivot is 1, the value to change into 0 is 5, so you get -5. Okay, so no changes on row 1. Okay, the pivot row will not change. So we just copy the whole row 1, 1, 4, -2. Row 1 plus row 2. So 1 plus -1, 0. 4 plus 6, 10. -2 plus 3, +1. Okay, then the second operation, -5 R1. So 1 times -5, you get -5. 5 plus 5, 0. Okay, 4 times -5, -20. -20 plus 2, -18. Okay, -2 times -5, you get +10. +10 plus 0. Okay. The next one. Okay, this is non-zero. Okay, whenever there's non-zero here, you have to go down and then suppose we need to turn right. So now this is your next pivot. Okay, this is your next pivot, and we need to change this into 0. Okay, so your M, negative fraction. What is the third operation? Right, over 5. Okay, your pivot is 10. you need to change negative 18 into 0. So you get a positive 18 over 10. So we simplify this, you get 9 over 5. Okay, 9 over 5. 9 over 5 are 2. Your row, your pivot from row 2 now, plus row 3. Okay. So no changes on row 1 and row 2. Okay, no changes on row 1 and row 2. You just copy the first row, the second row, then you change the new, you obtain the new row 3. Okay, for those who have done question number 1, you can proceed to number 2. For question number 2, we just need one operation. Okay. For the first stage, we just need one operation. Okay. Row 3, the first entry is already 0. Okay, this is already 0, so we don't have to do anything to the row 3. We just need to change this into row into 0. Okay, so the M is pivot is 3, put it at the bottom. We want to change the negative 2 into 0, so we have 2 over 3. Okay, 2 over 3, R1 plus R2. Okay, so only row 2 changed, row 1, row 3 remain the same. 2 over 3 times 3. Okay, and then plus to negative 2, you get 0. 2 over 3 times 8 plus to 4, you get 28 over 3. 5 times 2 over 3 and then plus 3, you get 19 over 3. Okay, you just follow the steps. Okay, so this is the next pivot, and we want to change this into 0. Okay, negative fraction. Pivot is 28 over 3. We want to change 1 into 0, so you have negative 3 over 28. Negative 3 over 28 R2 plus R3. Okay, so row 1, row 2 remain the same. That's what one just leave the reference. Actually, I'm going to use the reference. Otherwise, we will face problems in Gauss elimination. Okay, next we look at Gauss elimination. Okay, Gauss elimination, the basic idea is we solve the equivalence system, which is in a simpler form compared to the original linear system. Okay, what is this sentence means? Equivalence system. Okay, equivalence system. If you look at the example on the whiteboard, okay, this is a linear system. Okay, this is a given linear system. And this linear system, when we row reduce into this, okay, this is another linear system. But they have same answers. These two linear systems, they have the same answers. Okay, this one actually comes from here. Given a linear system, we can row reduce the linear system into an equivalent linear system. Okay, equivalent linear system means they have the same solution. They are equivalent. So when you have a simpler linear system, this one is in a linear, in a simpler form, right, compared to the original one. And from here, actually, we know what is x3, right? Based on this one, we know what is x3. If you know x3, we know what is x2. When you know x3 and x2 values, you know what is x1. So do you see the Gauss elimination now? When we row reduce into REF form, we can sort by backward substitution. We're starting from the last row, you solve for the last one, you get x3, and then up to here, you can solve for x2, and up to here, you can solve for x1. This is backward substitution. Okay, this is the basic idea of the Gauss elimination. Okay, so how to get this? Okay, how to get this? We look at the big picture of the flow first. Okay, the flow. Given the linear system, we can present the linear system in a matrix form. And from the matrix form, we can have the augmented matrix. Okay, augmented matrix, it means we combine the matrix A and also the vector B into one matrix. Okay, you see, this is a matrix. This is a matrix with a separator where this is the coefficients of x, y, z. This is the right-hand side value from the linear system. Okay, this is called augmented matrix. So basically, from the linear system, you can come up with the augmented matrix directly. You can skip this one. Okay, you can come up with the augmented matrix directly. And then you apply the row reduction. Okay, just now you have looked at how to row reduce a matrix without this. Okay, but now we have to row reduce the B together. Okay, that's mean you just ignore the separator. Okay, you ignore the separator. when this is multiplied to m and plus into the next row, okay, this one multiply m plus into the last row, the second row, right? Same goes to this, and you apply the same to the b. This one multiply to the same m and plus to row 2. Okay, we row reduce the matrix as if there is no separator. Okay, you just ignore the separator. Okay, row reduce the matrix. Then we apply the backward substitution. We will get the solution of x1, x2, x3. Okay, we look at one example. Okay, this one. This is a linear system. This is the matrix form. But actually, we can skip this. You can extract the A, the 2, 3, -1, 4, 4, -1, -3, -2, -3, and 4 as a matrix A, right? A, and this is the right-hand side value. You can come up with this directly. Okay, you can display the augmented matrix directly. Then we row reduce the matrix. Okay, so you see, this is the pivot. We need to change this one and this one into 0. So we have 2 operations. Okay, and you know how to come up with this one. Okay, so for example, this one, I take the first operation, negative plus to the second row. So 2 times -2 plus 4, you get. Okay, same as the working just now. 3 times -2, -6. -6 plus 4, -2. Okay, -1 times -2, +2. +2 plus -1, you get 1. And 2 times -2, you get -4. -4 plus -1, -1. So just row reduce and ignore the separator. Okay, ignore the separator, you just row reduce the right-hand side, this B as well. Okay, so when you get the new row, okay, by using this, row 1 plus row 3, so this one plus this plus this, this plus this, and this plus this, you get the new row 3. Okay, and after that, this is from row 1. Okay, if you look at this once again, this column 1 is from x1, column 2, x2, column 3, x3. So you can write x1, x2, x3 at the top. Okay, this means 0, we start from the last row, backward substitution, we start from the last row. This means 0, x1, that means 0, plus 0, x2, still 0, plus 3, x3, you get 3, x3, right, equals to 3. So you have this equation. Okay, so from here, x3 is 1. Then from the second row, you have -2 x2 plus x3 equals to -5. Okay, and substitute x1, solve for x2. And the first row means 2x1 plus 3x2 minus x3 equals to 2. Okay, so when you know x2 and x3 values, you know what is your x1. And finally, display your final answer in the vector form. Okay. Okay. Another example. Okay, second example, this one. Okay. So before you form the augmented matrix, okay, maybe you can check whether this follow the sequence x1, x2, x3, x1, x2, x3, x1, x2, x3. Okay, because it needs to follow the sequence. So 1, 2, 3, 2, -1, +1. Okay, and 3, 0, -1. And the right-hand side values 9, 8, 3. Okay, so once you come up with the augmented matrix, we will start to row reduce the matrix. Okay, so now you know how to get this. Okay, and this is the next pivot to change this into 0. So we need one more operation. Okay, then this is the RDF form. Okay, so last one, this is -4 x3. -4 x3. This is x1, this is x2, this is x3. So -4 x3 equals to -12. So your x3 is 3. Okay, your x3 is 3. Then -5 x2 minus 5 x3 equals to -10. Substitute your x3, solve for your x2. Your x2 is -1. Okay, and this one is 1x1 plus 2x2 plus 3x3 equals to 9. Okay, substitute the x2 and x3 that you obtain, solve for x1. Okay. Okay. Try this. Okay. Write out the amended matrix. You can insert the x1, x2, x3 at the top of the augmented matrix. Okay, x1, x2, x3. So start from the last row. Okay, start from the last row. We have negative half x3. Okay, negative half x3 equals to half. So x3 is negative 1. Okay, start from the last row. This is negative half x3 equals to half. And the second row is 14 over 3 x2 minus 7 over 3 x3 equals to 49 over 3. Okay, so substitute x3, solve for x2. Okay, so your final solution you display in the vector form. Okay, display your final answer in the vector form. Okay, any questions? This one you can try more exercise from the tutorial. Okay. And because I give only one exercise in the class. Okay, so if you want to have more exercise for your practice, try the tutorial question. Okay, next one. I want to give some introduction on the second method. Okay, some intro on the second method. Okay, LU decomposition. Okay, this is the second method. You're now given a linear system. Okay, look at the screen. Okay, given a linear system, AX equals to B, and we need to decompose A into LU. That's means we break A into matrix L and matrix U. So your A will be equals to LU. Okay. So when A is LU, that means AXB will be LUXB. Okay. And now the UX, this UX, okay, when we let UX be Y, okay, when this UX, we let it be Y, then we have LY equals to B. Okay. We let UX be Y, so LY equals to B. So we have these two. Okay, then we will solve LY equals to B for Y. Okay, that's means from here, you know you have the matrix L you have the vector B. We solve for y. That means y1, y2, y3 by forward substitution. Okay, once you get your y, then we solve for x. Because you have the matrix U, you have the values of y, you can solve for x. So this is LU decomposition. Okay, but today I will show how to decompose A into LU. Okay, the rest of this we will look at this on Thursday. Okay, so today we just look at how to decompose A into L and U. Okay. A square non-singular matrix. Okay, it must be a non-singular matrix. Must be a square matrix. Okay, for us to apply the LU decomposition. Okay, so this kind of matrix where all is leading principal minus. Okay, what is leading principal minus? Okay, this one. When you have 3 by 3 matrix, okay, when you have 3 by 3 matrix, you have D1, D2, D3. If you have 4 by 4 matrix, that means D1, D2, D3, D4. Okay, and the leading principal minus is, okay, for D1, we just take this. This is your D1. For D2, we take this. For D3, we take this. Okay, all starting from this corner. Okay, and we find for the determinant. Okay, except the first one, we just look at the value of A11. Okay, and the rest of this D, we look at the determinant of the portion of matrix. So all this should be non-zero. Okay, all this should be non-zero. Okay, then this kind of matrix we can decompose into L and U. The L is lower triangular matrix. U stands for upper triangular matrix. Okay. So for example, for 3 by 3 matrix, this is your L. Okay. Lower triangular matrix means the upper part must be all zeros. Upper triangular matrix means the lower part must be all zeros. Okay, and for L, matrix L, the diagonal entries are all 1. Okay, for this one, okay, for this L, the diagonal entries are all 1. Okay, so matrix A is given. You know all the values of this A. Okay, and we want to find for this L21, L31, L32, and all these U. Okay, we want to get the values of L and U to form the matrix of L and matrix of U. Okay, so this one, I repeat once again. A square non-singular matrix that satisfies the condition where all its leading principal minus are non-zero, okay, it can be decomposed into the L and U. Okay, it must satisfy this condition. Okay. So there are 2 methods to decompose A into L and U. This is the first one. Okay, this is the first method. I will call this as conventional one. Okay, the conventional one. This is your L. This is your U. So we know that L times U equals to A. So we find the product of these 2. Okay, so you multiply this matrix to this matrix. Draw column, you get this. Draw column, you get this. Okay, row, column, you get this. And then the second row, multiply to the first column, you get this. Okay, second row, second column, you get this. So one by one, you will get all these 9 entries. Okay, row, then column. Okay, so this is equals to this one. Okay, we know the values of all A. Okay, we know the values of all A. We look at this example. Okay, decompose A into LU. You have the values of A. Okay, this is your L, this is your U. After you find the product of matrix, you get this. So this is actually equals to the given matrix A. Okay, so now we want to find all the U and L one by one. Okay, so the first one, U11 equals to 1. Okay, here. U11 equals to 1, U12 is 4, U13 is 2. So we can get the U, this U values directly. Then this one, L21, U11 is -2. Okay, here, L21, U11 is -2. But you have already know what is U11. U11 is 1. That means you can find for L21. Then next, this one. This one equals to -1. Okay, here, this one equals to -1. And at this moment, you have already found L21 from here. And you know what is your U12 from here. Then you can solve for U22. Can you see that? Okay, one by one. So this one equals to 1. Okay. And you know what is L21, U13? Then solve for U23. Okay, same goes to this 3. Okay, this one equals to 4. You know the U11, then you can find for L31. Okay, so this one, you know this 3, you can solve for L32. Okay, and the last one, U33, is -1. So once you've found all this U and L, put them into this. Okay, L21 is -2, L31 is 4. Okay, L32 is -2. Your U11 is 1. Just take the values, put them into this to form your matrix L and matrix U. Okay, so this is the LU. We have decomposed matrix A into L and U, where L times U equals to A. Okay, this is the first method. Another method, we can use the row replacement operation. Okay, row replacement operation. Okay, so now matrix A satisfies the conditions where all its leading principal minus are non-zero. Okay, so this is the matrix. So you just row reduce, okay, using the ERO. Okay, we use only the row replacement operation. Use only row replacement operation. That means the NRI plus RJ. Okay, we use only that one to row reduce the matrix. And then one more operation, we get the REF. Okay, so this is your U. This is your U. This is upper triangular matrix, right? Then we have to find for this L. So how to get this L? Okay, how to get this L? So you see the relation. This one, the first pivot, the one that we haven't started to row reduce the matrix. The first pivot up to the last entry, everything must be divided by the pivot. So 1, -2, 4. Okay, all divided by 1, still 1, -2, 4. Then the second pivot is 7. Okay, second pivot is 7. And the one before, we take the one before the row reduction. We don't take this one. We take the one that before you use the pivot to change the underneath entry into 0. Okay, so second pivot up to the last entry at the bottom. All this must be divided by the pivot itself. So this 2 divided by 7, you get 1 and -2 here. And this is your third pivot. Okay, the third pivot divided by the pivot itself, you get 1. Okay, why all these are 0? Because this is lower triangular matrix. Lower triangular matrix, the upper part must be all zeros. And the diagonal entries are all 1. Okay, any questions? If no, we look at an example of 4 by 4 matrix. Okay, this one. So this one, this matrix satisfies the condition where all leading principal minus are non-zero. Okay, so here we can start to row reduce the matrix. Okay, so here we need 3 operations because we need to change this 1, 2, 3 into zeros. Then this is the second pivot. We need 1 operation to change this into 0, right? 1 operation to change this into 0. This is the next pivot. We use this pivot, okay, this operation to change this into 0. And finally, we get this. So this is your U. Okay, this is your U. So to get the L, okay, to get the L, this one divided by 1. Then you get here. The second pivot is here. So this one divided by -3. So 104. 104. And the next pivot is 2. Okay, divided by 2. So you get 1 and -2. And the last pivot is 1. Okay, so divided by 1, you get 1. So this is your L. Okay, you are free to choose any method to decompose the A into L and U. Okay. However, your matrix A must satisfy the conditions where all leading principal minors are non-zero. Okay. So for the method number 1 just now, method number 1, the conventional one, okay, actually it has no issues when the matrix A doesn't satisfy the condition. For example, this one. Okay, matrix A does not satisfy the condition to have a pure LU decomposition. Okay, since D2 is 0. Okay, this matrix D2 is 0. It doesn't satisfy the condition to have a pure LU decomposition. But still, this one, we can fix the problem by swap 2 rows, row interchange. Okay, if you look at this node, rows interchange, RK, change with RK plus 1 is applied when DK is 0. So the K here is 2, D2 is 0, so we swap row 2 with row 3. Okay, we swap row 2 with row 3. So this original matrix, we swap row 2 with row 3. So we swap before we start to row reduce. But remember this, when you swap, your B must swap as well. You have to swap your B. What is your B? Your B comes from the given linear system. Because to use this LU decomposition, you must be given a linear system. A linear system first, AX equals to B. And we deal on the A, we decompose A into L and U. And later on, we need to use the B from the question. So if you swap rows, okay, if you swap rows, remember to swap the B. Okay, remember to swap your B. Later on, you will need this B to proceed to get the answer for the x1, x2, x3. Okay, so this is what you need to remember. But if you use the conventional method, okay, you don't have to swap because you just compare, right? Compare both sides. There's no issue, something like this. Okay, so this one I continue. After we swap, okay, so we will start from this matrix, this matrix. So we just row reduce as usual. Okay, and coincidentally, by using this one, R1 plus R3, this one plus this, you get 0. And this one plus this, coincidentally, this is already 0. So we don't need one more operation because this is already the REF. This is the REF. Okay, so we stop here. This is your U. Okay, then for L, okay, this is the first pivot. So this column divided by 1, you put it here. This is the second. Okay, this is the second pivot. Okay, before any operation using this pivot, this already is 0. Okay, so this one divided by 10, so you get 1, 0. And the last pivot is 2, so 2 divided by 2, you get 1. So this is your L. Okay, so this is the difference between the conventional method and the row reduction to get the LU. So this one, you are free to choose any methods, either methods 1 or method 2 to get your L and U. But actually this one, suppose we need to check whether the D1, D2, D3 satisfy the condition or not, whether you get 0. Okay, but actually if you didn't check, okay, if you skip that step, if you didn't check whether it satisfies the condition or not, you go straight to draw reduce the matrix. Actually, you will know this matrix it doesn't satisfy the condition. By how? If you draw reduce this one, okay, if you go straight to draw reduce this one, you will find that the second pivot position, that value is 0, where you need to swap the non-zero to the pivot position to be the second pivot. Okay, you will find that condition. Okay, so even though you didn't check whether the matrix A satisfies the condition or not, if you go straight to draw reduce, you will still be able to know actually we need to swap. Okay. Okay, if you have a matrix something like this, when you want to do the row reduction, this one already 0, right? So you can sketch this. And next, we have to go down. We cannot cross this because this is not 0. So we have to go down. But when we go down, this one should be non-zero. So what we do, we have to swap row 2 with row 3. Okay, we have to swap. So that you have this 0, 2, 3, 0, 0, 1. After swap, okay, this is REF. So that's mean this kind of problem, this matrix, if you row reduce directly, you will see something like this. After you row reduce by using 2 operations, you will have a problem something like this. And by that time, you know, oh, I need to swap row 2 with row 3. I need to swap the non-zero up to this position to be the second pivot. So once you swap the row 2 and row 3, your V, okay, for example, originally your V is 1, 1, 3. Let's say this is your V. Then your new V will be 1, 3, -1. Because you swap the row 2 with row 3, so these two you have to swap as well. So later on, when you solve because after we decompose A into L and U, we will proceed to use the forward substitution and backward substitution. And we need this B. Then we don't take this B anymore. We will use the new B. If you swap here, you know what I mean? Okay, so if you didn't check for the condition, actually you can sense, okay, there is some problem here. I need to swap. Here I need to swap. That's it. Okay. So this one, actually, you can try this one. Okay, you can try on your own, try to row reduce and see what's happened. And if you use the first method, what's happened? You can spend some time to play around this. You want to try it now? I think we can try this now. We can simplify that. Okay, so when we row reduce, R1 plus R2, -4 R1 plus R3, Okay, so you see, suppose this is non-zero. Okay, so when we swap R2 with R3, okay, when we swap 0, 10, 9, 0, 0, 2, it means your B is supposed to be B1, B2, B3, but now we are using the new B, which is B1, B3, B2. Okay, so we don't use this anymore. We use the new B. Okay, so this is REM. Okay, this is REM. And if you want to test using the first method, okay, we haven't done. This is U. We haven't extract the information of L and U. Okay, so this is your U. Now what is your L? Your L must be something like this, right? Okay, what is the first column? This one, right? Divided by 1. Then? One? What one? This one? What is your second pivot? What is your second pivot? 2? Yeah. This is the one, right? So divided by 10. Divided by 10, so you get 1, 0. 1, 0. Okay, and the last pivot is 2. So 2 divided by 2, you get this 1. Okay, so this one, okay, I keep the L and U here. We try the first method. Okay, and we try the first method. Okay, so your U11. U11 is, okay, according to that matrix, U11 is 1. U12 is 4. Is it the same matrix? The same? I think different. Wait. 1, -2, -2. Oh, different. This is our A. Sorry, I'm sorry. Our A is this one. That's 1, -2, -2. 1, -2, -2. -1, 2, 4. 4, 2, 1. Okay. Then we try this. So your U11 is 1. U12 is -2. U13 is -2. 1, 3. Okay, next one, L21. L21, U11 is -1. Okay, -1. Your U11 is 1, so L21 is -1. Okay, L21, L21, U12 plus U22 equals to 2. Okay. L21 is -1, U12 is -2 plus U22 equals to 2. So that's mean U22 is 0. Next one, L21, U13 plus U23 equals to 4. Okay, 4. So L21 -1, U13 -2 plus U23 equals to 4. So U23 is 2. Okay, next. L31 U11 is 4. U11 is 1. So L31 is 4. Okay, this is 1. Next. L31 U12 plus L32 U22 equals to 2. Okay. 31 is 4. 1, 2 is -2. 3, 2, we need to find. U22 is 0. Okay, 0. So we can get find the L32. Wait. 31 U12 L32 U22 equals to 2. U11 is 1. Right? 4, 1, 2 is -2. 3, 2. 2, 0. Right? U22 is 0.
Answer L32 is 8. It has that. L32 is that.
Close to 1, 2. 1, 2, 3, 1, 2.
L32 is that.
We can't get to find L32. We can't get to find L32. Okay, let's check the last one. L31
U13.
U13.
13 is -2.
3
L32
U33. U33 equals to last one. L31 is 4. 1, 3. L32 U23 plus U33. We don't have U33, right?
No.
Okay. Oh, so this one, method 1, we can't have a pure LU decomposition. So you need to swap. Okay, you need to swap. So this one also, if you didn't check, okay, if you didn't check whether the all D is whether it's 0 or non-zero, if you proceed, you will face something like this. Okay, just like the row reduction. When you row reduce in the halfway, you will find that the pivot position is 0. Where you need to swap. Okay. So this kind of case, you need to check first. Okay, D1, D2, D3. Okay, unless you want to try first, then you need to spend time again after you swap. Okay. Personally, I think that the second method is easier, right? Yeah. Because after swap, you just swap the B. This one also, if you swap here, B also you need to swap. Okay, because the linear equation before the linear equation number 2 swap with number 3, the B must swap. Yeah. Okay. So on how to solve the linear system by using LU, we will look at it in the next class. Okay. Okay.